Okay, so we're taking a look at calculus. We're looking at now our section 4.2, what the derivative tells us. Okay, so as we look at what the derivative tells us, it starts talking about the increasing and decreasing functions. Suppose a function f is defined on interval I. We say that f is increasing. Then they also talk about decreasing. So what this is starting to imply is that when we start working with our first derivative, we talk about the test for intervals on increasing and decreasing. So if f is continuous on interval I and differentiable at all points of the interval I, when the derivative function is greater than 0, so we see right here that f prime of x is greater than 0, at all interior points of f, then f is increasing on the interval. And when the derivative is less than 0 on all points, that's when we talk about that we're decreasing. So once again, I have some pictures above here. We talk about as we take the derivative and we plug these values in, we see we got positive values. So we see the slope of this tangent line right here is positive. Because it's positive, we have increasing values. Over here we talk about when the first derivative of this right here, we plug the values in, we get a decreasing slope or a negative value of it. So that talks about that we're decreasing in value as we go. As we continue on, we talk about the first derivative test. Okay, so on the first derivative test right here, we talk about, once again, that we have a continuous interval and that it's also differentiable on this point value. Given all this, if f prime changes in sign from positive to negative, we talk about a local maximum. If it is negative, so we're decreasing, and then all of a sudden we're increasing, we have a local minimum. And if f prime is the same sign, well then we don't have any local extrema. So basically, as we start going through point values, we start recognizing that what's happening with our slopes, and if our slopes are changing in values, then we see that we have our local maximum minimums. The next thing we start talking about is one local extrema implies absolute extrema. So we look at right here, if local maximum occurs at C, then f of C is an absolute maximum, plus then if local minimum occurs at C, then f of C is an absolute minima. What this is talking about right over here is basically that we could section off any graph then on a different interval, and then on this interval from right here to here, this would be an absolute minima, even though the graph itself as an entire function would have different ones. We just start limiting down our intervals. Next thing we start talking about is concavity. Okay, so when we start talking about concavity, we're talking about the curvature that's happening. So basically we talk about inflection points. So once again, when we have concavity, we're relating that curvature of our graph. So for example, if we were to consider, just grab a piece of paper here, if we were to consider a curvature, let's just go like this. Okay, as we see that we'd have kind of like a cubic graph right here, we would see that all this curvature right here is kind of curving downward to this point right here. So it'd be reflecting kind of to that central point. But the moment we get here, all this stuff would start curving the other way. So right here is where we would see that that concavity is changing from being concave downward to concave upward. So that's what this second derivative test is starting to imply for us. It's saying let f be differentiable on an open interval. If f prime is increased on the interval, then f is concave up. Once again, if our values are relating in here, then we have our concavity. Talks about as f prime is decreasing, then we're concave downward. So once again, they're talking about how this slope happens and how it goes. Then we start talking about our inflection points in here. So kind of coming over here, we talk about the test for concavity. The test for concavity, it says suppose f double prime exists on an interval. If our value, when we plug in an x value into our double derivative or a second derivative function, is greater than 0 or positive, then we have a concavity upward, or we're concave upward. If it's negative in that second derivative, then we have a concave downward. And once again, if C is a point at which I have to change its sign at C, so once again, we start looking at when does that second derivative equal 0. When that second derivative equals 0, that's when we start talking about this point right here where we change from concave downward to concave upward, or concave upward to concave downward. That would be starting to consider our inflection points. Okay, so one of the things to also be careful on here is that we see that inflection points, like right here, we have an instant change in our reflection points. Right here on this one, there is no second derivative equals 0, but it's not an inflection point, once again, because we stayed positive to positive. Down here, we see that our derivative doesn't exist, but yet we still have a concavity change for an inflection point. And then not an inflection point because concavity, once again, does not change, kind of like this one was up here. We don't have any change in concavity, so it's not considered an inflection point. That should kind of sum up basically, once again, that second derivative test. Also tells us, so if we think about any point in the second derivative, so rather than trying to figure out whether we're increasing or decreasing on that first derivative, what we start looking at is we start looking at that second derivative, and if we imply that then the second derivative value right here is greater than 0, then it's a local minimum, because once again it's concave upward. And if it's less than 0, it's concave downward, and once again, if it equals 0, then the test is inconclusive for this part of it. So kind of recapping what's going on here, looking at these graphs that they gave us, we talk about that we have differentiability in different ones, open intervals. As we look through, we see that some have local maximums, some have local minimums. As we look at concavities, then we have inflection points, or we just talk about whether we're curving upward or downward. Once again, when you think about the curvature, my advice to you would be thinking about if you were to throw a ball at it, what way would it be bouncing back? Once again, as the curvature of the graph, as you're inside the graph, how are things changing?